So for our second talk of this morning, we're very pleased to have Andras Juhasz. The title of his talk is Signature, Cusp Geometry, and Machine Learning.
Thank you. Can you see it in full screen?
Looks great.
Yeah, okay, thank you. It's doing some weird things. Okay. Right, so this is a project where we used machine learning as a tool to find an interesting relationship between the cusp geometry of hyperbolic knots and its signature. And what I'd like to focus on is the process that we used in order to find these results, as this is a technique that we believe can be useful in other areas of mathematics. So this is joint work with Alex Davis, Mark Leckenby, and Nenad Tomashev, where Alex Davis and Nenad Tomashev work in machine learning and DeepMind. Okay, so let me quickly recap some hyperbolic invariants of knots. So let K be a hyperbolic knot in the tree-sphere, which means that its complement has this complete finite volume hyperbolic metric. And one of the fundamental invariants you can extract is, of course, the volume. So by most of rigidity, the hyperbolic metric is unique up to isometry, and whatever geometric quantity you define using that metric will be a topological invariant of that knot. Now, if you take a maximal cusp neighborhood of your knot, this is like a tubular neighborhood of your knot, then you look at the boundary that will be a Euclidean torus, which you can view as the complex plane quotiented out by some lattice lambda. And if you take the longitude of your knot and lift it to C, then you can normalize things that it runs from 0 to a positive real number lambda, and this positive real number is called the longitudinal translation of your knot. And then similarly, you can lift the meridian starting from the origin in the complex plane, and it ends at some complex number mu, and we can assume that it has positive imaginary part, and this is called the meridional translation. So this lattice lambda is generated by lambda and mu. So our goal when we started out was to find some relationship between the hyperbolic and, say, four-dimensional knot invariants, where by four-dimensional knot invariants we looked at things like signature and various Hagar-Floer invariants like tau, nu, epsilon, and then maybe the Kovanov S invariant. And we found various relationships, but somehow the strongest signal was between the cusp shape and the signature. And signature is, of course, the easiest to compute of all these invariants. So the data that we looked at initially was from the KnotInfo dataset, which contains knots up to 12 crossings, and then later at the Regina census, which has knots up to 16 crossings. And then we also generated these random knot diagrams using SNAPy of 80 crossings when you apply SNAPy simplify. Of course, you might have some duplicates, but you can get rid of these by using various knot invariants. So this was a data set of 10 to the 6 knots approximately. And so what we used was a supervised learning model to detect patterns between a large set of geometric invariants and the signature. So supervised learning, what it means is you have a data set, you want to predict maybe B from A, and so basically you are trying to approximate a function the simplest example would be maybe linear regression, where you're just trying to fit a line. But there are more advanced models going up to neural networks where you have highly non-linear things that you are trying to fit on your data. And so you take part of your data where you can test how good your approximation is. So you need some metric, maybe an L2 metric, by which you measure error of the model or the approximation that you got. So for those of you who are interested in the technical details, what we used was a fully connected feed-forward neural network with 3 hidden units of size 300 each. So what this is just like a composition of linear maps between vector spaces of dimension 300 in the middle, so like large matrices, and there is some non-linearity that you have to apply. And what the training of such a model does is you do sort of gradient descent to try to optimize the coefficients of these matrices so that the error is as small as possible. Now, here is an example of some of the geometric quantities that we considered. And so remember, we were trying to predict the signature. And then there are the so-called attribution techniques, which are also known as saliency maps, where you can figure out which of the features, input features, so which quantities are most predictive of what you are trying to estimate, namely the signature. And basically you are just taking partial derivatives with respect to these quantities. And it turned out that the 3 most predictive ones were the imaginary and real parts of the meridional translation, the longitudinal translation, and then there was weaker signal in the complex length of short geodesics and the injectivity radius. But this sort of seem like they are less important, but you will see later that actually they turned out to be crucial to finding the right conjecture. So this is like these gradient-based techniques for finding what are the most important quantities that predict the signature. So you have these very complicated functions and these lots of variables, and so we found that it's the longitudinal and meridional translation which determine the cusp shape that somehow tell us something about the signature. So then we plotted the most salient features versus the signature and colored by the slope, volume. And we got this rather curious plot. So we use volume here, but you could also take crossing number. They are sort of equivalent. And as you can see, there is some nonlinear relationship between the real part of the meridional translation, the signature, and the volume. So this is on a large data set of hyperbolic knots. And there are various things you might conjecture. The crudest thing would be there is some relationship between the signs of the real part of the meridional translation and the signature, which actually turned out to be false. So then if one writes down the following quantity, which we call the natural slope for a hyperbolic knot, is you take the longitudinal translation divided by the meridional translation and take its real part, and we call this the natural slope of the knot. So there were some similar quantities showing up in earlier work, but like exactly in this form, this is kind of new, but it quantifies the shape of this lattice that determines the cusp. And here is a more geometric interpretation. So here is the cusp torus, and you take a meridian, and then you go along an orthogonal geodesic starting from the meridian, and you come back, you go around the longitude, and you hit the meridian again at some point, which might not be the exact same point. And so by the time you return to the meridian, you have traveled one longitude minus some multiple s of the meridian. And it's a simple exercise to show that this s is the natural slope of your knot k. Now, if you plot signature versus slope, now you can observe an approximately linear relationship between the slope and signature. So this is for random knots for 10 to 80 crossings. When I take, crossing number, I mean the crossing number in the snappy simplified form. The actual crossing number, of course, might be smaller. And the question is, what's the error? I mean, clearly there is some error term. And so our first conjecture was that the difference between twice the signature and the slope is some linear function of the volume of your knot. And this was supported by several large data sets sampled from different distributions. So it seemed like, this must be true. But actually, we managed to obtain counterexamples using highly twisted knots that I'm going to talk about in a second. But so this is actually an important caveat whenever you try to conjecture something using large data sets. There might be some counterexamples lurking in some non-generic family somewhere. So statistics is a strange thing. Now I should mention that we still believe that asymptotically, almost surely, this twice signature minus the slope can be bounded by a linear function of square root of the volume. And there is some reasonably good heuristic why that should be the case. So for a generic knot, this would be true. So I mentioned these highly twisted knots. It's a bit technical to state, but it's not so complicated. So we take a knot, and we take a collection of unknots C1, Cn in the complement of your knot that bound disjoint disks. And suppose that if you take your knot together with these circles C1, Cn, that's a hyperbolic link. And now we denote by K of Q1, Qn to be the knot obtained by adding Qi full twists to the strings going through Ci. And if Li is the linking number between Ci and the knot for some orientations, then some of these Li's will be even, and we can assume that the first M of these are even and the rest are odd. And so the statement is that there is some constant K, which depends on the knot and the circle C1, Cn, such that for Qi sufficiently large, the slope plus sum of Li squared times Qi in absolute value is at most K. So this shows how the slope changes asymptotically as the number of twists gets very large. And on the other hand, the signature changes by a slightly different quantity, which is shown here, where you have to take into account whether your linking number is even or odd. And so this allows one to construct knots where you introduce many twists, and the difference between the signature and the slope will not be bounded by the volume, because if you do this twisting, then the volume doesn't change, let's say it remains bounded. Right, so what is the theorem that we managed to prove? Well, first let me define the injectivity radius of a knot. And this is defined to be, you take your knot and you remove the maximal cusp n. And then you take the injectivity radii of the points of this remaining manifold, and you take the infimum of that. And so the theorem is that there is some constant such that for any hyperbolic knot k, twice the signature minus the slope is bounded from above by constant times the volume divided by the cube of the injectivity radius. And the C1 is the same as C. That's a typo. So what do we know about this constant? We know that it is at least 0.2339. But more interestingly, it seems that this constant is not very large, and the largest value we managed to obtain using these highly twisted knots, namely some family of certain braids, was 0.234. So we sort of based on this conjecture that maybe C is at most 0.3. So it's fairly small, but like it would be very interesting if one could show that we have this constant. And so let's look at some examples. Here you can see a 12 crossing knot, and on the right is cusp torus as drawn by Snappy. And so the longitude has length 27.7 approximately, and here is the meridian. And so from this you can compute that the natural slope is minus 18.6 approximately, and this signature is minus 8, which is indeed, you see, twice the signature is close to the slope. And you can note that, so in this picture in purple, you can see the fundamental domain of this lattice, and this is a very skewed parallelogram. So this is very far from being right angle, and that's exactly the defining feature of having very large positive or very large negative slope. So this has some simple applications, this theorem. Ian Agol and independently Mark Leckenby showed that if S is a surgery slope for a knot that has length greater than 6, then S is not an exceptional slope, which means that the infilling or the surgery with this slope gives you a hyperbolic 3 manifold. And using that, one can show that if K is a hyperbolic knot and P over Q is a slope that satisfies this inequality, so it's not too far from the signature, the error involves the volume and the injectivity radius, or the modulus of P is greater than 8, then P over Q, the insurgery along your knot, gives a hyperbolic 3 manifold. So here, this condition on P being bigger than 8 uses a result of Leckenby and Meyerhof. So this is something that, to our knowledge, hasn't been observed so far, that exceptional surgeries are somehow centered around twice the signature. So here is an example. If you look at 12 and 242, right? Which is what we looked at before. It has 7 exceptional slopes listed here. They all lie in the interval 16, 20, which contains both minus the slope and minus twice the signature. Now, since the slope, the signature gives the lower bound on the topological 4 genus, if we reverse this theorem, we get that using the hyperbolic geometry, namely the slope, you can get a lower bound on the topological 4 genus, which is also kind of surprising. Okay, so let me say a few words about the proof of this main theorem. This was shown you by constructing a nice spanning surface with the specified slope along the boundary torus of the knot, which is of independent interest. So there is some constant such that for every hyperbolic knot, there is an unoriented spanning surface F for your knot K, whose Euler characteristic has absolute value at most constant times the volume divided by the cube of the injectivity radius. So it's like, and furthermore, the boundary slope of the surface is n, where n is a even integer closest to slope k. So it gives some information about the cross-cap number of the knot if you fix this specific boundary slope. And this is shown by constructing a nice triangulation of the complement of the maximal cusp neighborhood, where the number of tetrahedra is bounded by the volume of the knot and the injectivity radius. And then to obtain this theorem relating signature and slope, one uses the Gordon-Liderland signature formula. So the boundary behavior comes in from that formula, because when you take the signature of the Goeritz matrix, then there is also a term which measures the normal Euler number, and so this is given by this natural slope, or at least this closest even integer. Right, now if you don't like the injectivity radius showing up in our bound, there is a refinement of this inequality which uses short geodesics. And I should mention here that remember that when we looked at the most salient, the most important features that determine signature, there was the meridional translation, the longitudinal translation, but then the next two were injectivity radius and short geodesics. And in fact, injectivity radius showed up in our bound, and now short geodesics showed up here. So it would have saved us a lot of time if we actually followed what the machine learning was telling us in the beginning. So let odd geo epsilon over 2 denote the set of geodesics in the knot complement that has length at most epsilon over 2 and have odd linking number with k. Actually, if you compare this with the previous result about how the signature and slope change when you do twists around circles that link your knot, there was a distinction between even and odd linking. So this is related to that. And furthermore, let for integers p and q, kappa of pq will be the signature of the PQ torus knot plus P times Q over 2. So this is a signature correction term, which I think goes back. It can be computed using a simple recursive formula by work of Gordon and Liderland. And for a geodesic gamma, there is this slightly complicated quantity. It's a pair of integers, twist p gamma and twist q gamma. It's a pair of coprime integers p and q such that p is even, q is odd and non-negative, and subject to this condition, if you take the complex length of gamma times p plus 2 pi I times q, this is minimized, where the complex length of gamma is this geodesic has real part the actual length, and then the imaginary part measures the twisting around the geodesic. So we choose a PQ that is minimal with respect to the lexicographical ordering if it's non-unique. And so here is the refined theorem, which says if epsilon 3 is the Margulis constant, which shows up in the thick-thin decomposition of hyperbolic manifolds, and epsilon is a positive constant which is less than epsilon 3, then there is some constant C4 which depends on this epsilon, such that for any hyperbolic knot K, signature and slope over 2 minus the sum over these odd geodesics of length less than epsilon 2, this kappa of these twisting parameters. These differ by at most constant times the volume. So here the upper bound doesn't depend on the injectivity radius anymore. And so what these kappas do is, if you sort of remove neighborhoods of these short geodesics that have odd linking number with your knot, and you construct some surface which along the boundary of the knot has slope, the natural slope basically, then you can fill in with a surface that will contribute this kappa twist p, twist q to the signature of the Göritz form. So that's why this shows up here. Okay, so that's what I had in mind today.
Let's thank Andras.